Okay, so here are the two examples. I might be able to get them on one tape. That'd be awesome. Okay, so to start with here, we're looking at air that's entering a turbine. So automatically, we know we're an open system because it's a turbine. Steady state, which means that we know that the inlet and exit mass flow rates are the same. We've got some information about inlet and exit, which I've listed down here, our pressures and temperatures at the inlet and exits. And we know that we have an average boundary temperature of 315. What else do we know? Mass flow rate, do we have that? No, heat transfer at a rate of 30 kilojoules per kilogram. So remember what that is. Normally when we talk about rates, it's per time. Here it's per kilogram. So really what it is it's kilojoules per second over kilograms per second. And so the per seconds cancel. So just remember, this is something that we need to know to do anytime we see this kind of unit. All right, what else do we know? We know it's air in an X is an ideal gas. We know the specific heat, and we know that we're not going to be concerned about kinetic and potential energy effects. Is that everything? What are we trying to find? The rate of power developed, again, per kilogram. So again, that same sort of W dot over M dot. And then additionally, the entropy production. The rate of entropy production, which is the same thing, sigma dot over m dot. Okay, so let's start thinking about how we're going to solve this. So let's look at some equations. So the equation, that I always start with is going to be our energy rate balance. And I'm a little bit sloppy here about writing kinetic and potential energy. I'm not writing all the details because I know that these are going to be zero. I still like to list them just to remind myself that I am neglecting those effects, just to remind myself that that's an active choice that I'm making. And as you get further along in your career, you'll have to be more careful about that. You can't always just disregard things that we do typically in a first semester class. And then I've also used 1 for the inlet and 2 for the exit. Okay, so the next thing I'm going to do is I need to solve for W dot over M dot. So we'll come over here, W dot. I need to divide everything by M dot. And so that means I'm just going to cancel this out. So I have what I'm looking for. I have this quantity here already. So really, I just need H1 and H2, and I didn't really leave a lot of space. So again, I encourage you to leave space at the end of your tables. So what table am I looking at? I've got air, and I have the temperature, so I believe that I'm looking in table A22. And so those values are 1011.9 kilojoule per kilogram. Oh, and I have a note that I made that this was an average because in the table, let's take a look. We don't find 970. So let's just take a look at what we do find in the table. A22. A22. Like a football player. A22. A22. Mike. Okay, so here, I don't know if you can see here. I can't see that far. I don't know if I can get all the way over there. So here we have 960 and 980, so we're just going to take the average value for the entropy here. And then we'll do the same thing with 670, we'll have the same issue. Is that true? No, 670 is in the table exactly. Okay, so this one is an average value. It's exactly in between the two values in the table. And then this one's 681.14, same units. Okay, now we're just ready to plug everything in, so that's pretty easy. So negative 30 kilojoule per kilogram, that is the correct unit, plus 1011.9 minus 681.14. Those are also in kilojoule per kilogram, so everything's in the correct units already. So I get 301 kilojoule per kilogram. So that is our answer then. Okay, could we do this another way? And the answer is yes, we do have some information additionally. Here's another plan of attack. The other thing that you can look at is because it's an ideal gas, we know that H1 minus H2 is equal to C sub P T1 minus T2. So this is going to replace just this piece right here. So that piece then, we know the specific heat, kilojoule per kilogram, and then we know T1 minus T2 is 970 minus 670, so this gives us 330 kilojoule per kilogram. Kilojoule per kilogram, or you can't see, I apologize. Okay, and so now we're just going to drop this here into this equation, so it's going to be 330 minus 30, so here I'm going to get, I don't know if you can see it, 300 kilojoule per kilogram. Let's see if I can make this just almost. Almost. Oh my goodness, really? All right, there we go. So again, dramatically the same. Okay, so we'll leave that one there. All right, so now let's looking at the second part, which is to find entropy production. So I'm going to hold this over here in case I need to refer to some things. So entropy production, this is again number 87, B, entropy production. So for the first one, when we were looking for work, we used our energy rate balance equation. This time we're going to use our entropy rate balance equation. So for an open system at steady state, we have the following. Where again, that's inlet minus exit. Okay, we're going to solve for the rate of entropy production. But again, we needed it in a per kilogram basis, so now I'm going to divide everything through by that. So that's going to cancel. And so here we're going to have, I'm going to put it right here. So that's fortunate because we have all of these quantities. We have Q dot per M dot, we're given that. We have the boundary temperature, and then we can look up those. Okay, so we can look those up, but because it's an ideal gas, we'll use one of those ideal gas equations. So I could look up the S zeros, but I'm not going to. I'm just going to use the equation that has to do with the change in temperature. And in this case, because I know pressure, so this is important, the two different choices I have depend on what I know. I either know temperature and volume, or I know temperature and pressure. So here I know temperature and pressure, so I will use that equation for ideal gases. Okay, so let's see. Let's go ahead and write this out a little bit more clearly. So I have this quantity. I know I say not to use slash fractions, but I'm going to leave that there like that. Plus, and now I'm going to use, oh, and I did make a mistake in copying. I did change the order of this rather than having a minus sign. I changed, see, it's just like class. I'm using whiteout. So that'll be S2 minus S1, and that's important because it matters the order of things. So this component here, this part here, I'm going to write as C sub P ln of the change in temperatures, that ratio, minus R times ln the ratio of the pressures. So that is that component. And again, this was, I changed the signs on that. I mean, I changed the order on these just simply because when I subtracted it to the other side instead of the minus sign, I just switched the order. Okay, so I have everything. So now it's a matter of plugging in. Oh, I did not write down R, so I'm going to come back to our front page and write down that R is equal to 0.2870 kilojoule per kilogram Kelvin. Okay, so now I have everything. So just dropping in everything here, minus negative 30 kilojoule per kilogram, times 1 over the temperature, plus the specific heat, times Lin ratio of the temperatures. And here I'm not going to bother to put in the units for temperature because of course they're going to cancel. Minus 0.2870 kilojoule per kilogram Kelvin times, I'm running out of space to write, I'm going to shift just a little bit, Lin 100 over 400. And again, I'm not writing the units on the pressure because I know the ratio will cancel. So altogether, when you crunch all those numbers, 0.086 kilojoule per kilogram. And that would be energy production, rate of entropy production per kilogram. Okay, so, and I'm realizing I'm probably standing right in front so you can't see, so let me back up so you can see everything. Okay, so what, let's just kind of review how this problem goes. So we start with, we know we have an open system that's at steady state, and we have air as an ideal gas. So importantly, we're going to write down our table of inlets and exits just like always. Leave a little space, which I did not. We're going to look up our values in table A22 when we can. To find work, the first thing we're going to do, remember again, anytime it's kilojoule per kilogram, we know we have to form the ratio of the rates, and the time component drops out. So here, I'm going to start with energy rate balance, ignore KE, PE, divide, solve, plug in. That one's pretty straightforward. And then to find entropy production, way down so I can point. Again, we're going to start with our entropy rate balance, solve for sigma, divide by the m dot, so we get an m dot there and that one drops out. Because it's an ideal gas, so remember we have equations that look similar to this for incompressible substances. This is not, this is ideal gas. So here we're going to have, for this ideal gas change in entropy, we're going to use this. We could instead have looked up in the table for air and done the S zeros, S20 minus S10, that would be okay as well. And then drop in all the numbers, all the units work really nicely here. And for the most part for these ones they do. There's just not a lot of unit conversion. Okay, so one more problem. Now, this is a heat exchanger problem, so lots to write down. Lots and lots to write down, so let's take a look. All right, so saturated water vapor. Actually, before I do that, let me check how I'm doing for time.